So good morning, everyone. I'm Amritesh and my PhD advisor is Dr. Sanjay K. Banerjee.
I'm Maruthi Yogeesh, and my PhD advisor is Professor Deji Akinwande.
And today we are really excited to walk you through our innovation proposal titled Ultra-Low Power Devices Based on van der Waals Heterostructures. So let me briefly talk about the outline of our talk. We'll start with the motivation that why there is a need for such ultra-low power devices. Then we'll look at some tunneling devices in comparison to CMOS. Then we'll introduce what 2D materials are and what advantages they have over 3D materials. Then we'll also look at some tunneling devices based on these 2D materials and talk about what the state of the art is. And then we'll talk about not just one, but two innovation proposals based on heterostructures of these 2D materials. So as we all know that CMOS devices are being made smaller and smaller in accordance with Moore's law to make electronics better, faster, cheaper. But as the technology node scales down, the overall chip power density keeps increasing. In fact, the power density of the chip was expected to reach that of a rocket nozzle and even that of the sun. So much is the emphasis on power dissipation in today's chips that it was used by you guys in your famous butter benchmarking test to show that your Snapdragon processor melts the least amount of butter in comparison to your competitors. But the whole idea now is to make sure that our computer chips don't end up becoming frying pans. And therefore, we must look at the root of this problem. And because transistors are the root of all electronics, therefore, there's a need to explore energy-efficient, ultra-low power beyond CMOS device concepts. So talking of beyond CMOS device concepts, the tunnel field effect transistor is one such promising ultra-low power device that is widely being pursued by industry and academia. It features the mechanism of band-to-band tunneling of electrons that enables the tunnel field effect transistor to achieve a subthreshold swing lower than 60 millivolts per decade, thereby enabling low power operation and better performance at low VDD as compared to CMOS. But the experimental results so far based on tunnel FETs based on heterostructures of these 3D semiconductors, such as silicon, silicon germanium, and 3.5s, they lag the projections. And that is because of several non-idealities, such as band TSG to phonons, defect-assisted tunneling, interface, border traps, and so on. In fact, if you look at this plot over here, which is a compilation of experimental TFET results, you can see that devices that have good on-state performance have extremely poor subthreshold swings, whereas devices that have decent subthreshold swings have extremely poor on-state performance. Besides, 3D materials suffer from an inherent scaling issue, and 3D heterostructures suffer from strict lattice matching issues.
So this brings us to discuss the advantages of the 2D materials over 3D. We are familiar with this 2D material graphene, which is metallic in nature. There are also a host of 2D materials which are semiconducting in. And the most popular among them is the transition metal dichalcogenides, or what are known as TMDs. These are materials which have a very diverse band alignments. They are characterized by atomically very thin body and have a very sizable band gap, which is advantageous from scaling point of view compared to 3D. The most important property of this 2D material is the absence of dangling bonds, which is you can find it in 3D materials, and also between the layers of the 2D material, you have the van der Waals bonding between the layers, which alleviates the lattice mismatch issue. These two important properties, like absence of dangling bonds and the presence of the van der Waals bonding, helps us to design van der Waals heterostructures with very minimum traps. And this is the main advantage why we are interested in 2D materials as compared to 3D. So the Esaki tunnel diode is the main core enabler of our tunnel FETs, what was mentioned by my friend. It features this negative differential resistance, or NDR, and this happens due to this phenomena of band-to-band tunneling. Many research groups have already shown this Esaki type NDR in 2D van der Waals heterostructures, as shown above here. But the point to observe here is that the NDR which has been shown is either at low temperature like 77 Kelvin, or they have shown it with 2D materials which are not environmentally stable, like for example, black phosphorus, or the materials for which there are currently no large area growth techniques. So we propose here a room temperature NDR in a molybdenum-based Esaki tunnel diode. And our particular van der Waals heterostructure is comprised of the molybdenum ditelluride, hexagonal boron nitride, and molybdenum sulfide. MOTE2 and MOS2 are the two semiconducting van der Waals semiconducting 2D materials, and HBN is the 2D insulator whose advantage my friend is going to talk very shortly. We have selected this particular platform. The main reason behind it is both MOTE2 and MOS2 are environmentally very stable. There are currently large area growth techniques for all these materials in our platform. So we can take this proof of concept device towards the wafer scale production, which is very important from an industry point of view. And most important is that this particular platform is CMOS compatible. So it can basically complement the existing silicon technology, as mentioned by Rashid in his inaugural address of 3D IC. So we can have a heterostructure integrated with the silicon CMOS.
Okay, so now take a look at our first innovation proposal, that is demonstration of the room temperature Esaki tunnel diode based on a heterostructure. So our heterostructure stack will be assembled from exfoliated flakes using hemispherical PDMS stamps. This technique will allow us to very precisely pick up and transfer flakes on top of each other. Now let me quickly walk you through our fabrication procedure. So we'll start with a silicon dioxide substrate, onto which we'll pattern the bottom gate for the MOS2 as well as the bottom contact for the MOTE2. Then we'll put down a heterostructure stack comprising MOTE2, interlayer HBN, and MOS2. And finally, we'll end up with the top gate for the MOTE2 and the top contact for the MOS2. Now, a heterostructure features a dual gated overlap region between the MOS2 and MOTE2. And these dual gates will allow us to independently tune the carrier densities, in our case, electrons in the MOS2 and holes in the MOTE2, as you can also see from the band diagram of the system right over here. Now, the role of the interlayer HBN would be extremely critical, as it'll help us in unlocking the band alignments of the MOS2 with respect to that of the MOTE2, thereby allowing the two bands to move relatively freely with respect to each other, which will help us in creating a type 3 broken gap junction that is necessary for achieving room temperature NDR in the forward bias characteristics of this device. Now, a couple of points I'd like to mention that although we'll be using exfoliated flakes, but as we mentioned, large area growth techniques are already available for for all the materials that we are going to use. And indeed, this particular heterostructure device can also be used to explore its tunnel fed behavior. But we want to use this heterostructure platform to explore a very novel, ultra-low power, and beyond CMOS device concept based on completely new physics. And that is our second innovation proposal. That is demonstration of the bilayer pseudo-spin field effect transistor, or the BISFET, a device idea that was born at UT Austin but hasn't been experimentally demonstrated yet. So what exactly is the BISFET? Well, it is based on the idea of room temperature superfluid exciton condensation in 2D systems with adjacent N-type and P-type layers. Let's look at the mechanism of its operation. So if we have electrons in one layer and holes in the other layer, and if the carrier densities of the two layers are balanced or matched, then these electrons and holes can form exciton pairs that can condense. And upon the application of a very small interlayer bias on the order of kT over Q, it results in a many-body tunneling current that has an NDR in its characteristic. And this many-body NDR can be used as a novel switch. Theoretical calculations have predicted the NDR switching energies to be on the order of tens of zeptojoules that can afford BISFET-based logic gates about 2 to 3 orders of magnitude switching power reductions than end-of-the-roadmap CMOS. And interestingly enough, the exciton condensate has been predicted in our heterostructure system very recently. Now, one of the most important techniques to try and detect this exciton condensation is called the Coulomb drag. So what exactly is the Coulomb drag? Well, it originates from interlayer electron-electron interactions and is defined by something called the drag resistivity. In this technique, we pass a current through one 2D layer that induces a voltage in the adjacent 2D layer, thanks to Coulombic interactions of the charge carriers. Now, if the exciton condensate forms, then the drag resistivity should jump to a value comparable to the isolated layer resistivity. In our case, we'll use a modified heterostructure platform with multiple contacts to each layers to do temperature-dependent Coulomb drag measurements. And these drag studies will help us optimize our heterostructure platform for the realization of the BISFET.
So now this brings us to look at the facilities at UT. We have a novel pick-and-place probe station for fabrication of the heterostructures. We have this Cascade and the Lakeshore probe stations for doing low-temperature, high-vacuum electrical measurements. We are also having the quantum physical parameter measurement system to do the Coulomb drag measurements at low temperatures under high magnetic fields. So UT has a world-class clean room facility with silicon device fabrication and also nano characterization tools available. So this is the initial results we want to show here. We have already started working on these heterostructures made of MOT2 and MOS2. We have demonstrated the PN junction diode using those heterostructures, and these results were recently presented at the APS March meeting, and we want to go to the next step of Esaki tunnel diode and towards the BISFET.
So finally, to summarize, computer chips are getting hotter and hotter, so we need beyond CMOS ultra-low power device concepts. Tunneling devices such as the TFET offer an attractive alternative, and 2D materials have significant advantages over 3D when it comes to making these heterostructure tunneling devices. Our goal is to use the heterostructure platform of MOT2, HBN, and MOS2 to demonstrate not just the room temperature Esaki tunnel diode, but also the BISFET, which is a very novel ultra-low power device. Now, we should put our money where the miracle is, and we believe that the BISFET is one such miracle device concept. And if realized, it can be a complete game changer for the electronics industry. Here's our one-year project timeline. So in the first half, we'll try to demonstrate the room temperature Esaki tunnel diode. And in much of the later half, we'll do temperature-dependent Coulomb drag measurements to try and detect the exciton condensate. And later on, we also plan to design and fabricate some simple NDR-based circuits based on our devices. Here's our team. We have two world-renowned professors, Dr. Sanjay K. Banerjee and Dr. Deji Akinwande. They've made some very important contributions to CMOS technology and emerging nanoelectronics. And both of us have the expertise in the design, fabrication, and characterization of 2D materials-based devices. And we believe we have the right firepower to implement our proposal. With that, I'd like to thank everyone, and we'd be happy to take any questions.